Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Up to now, when we talked about limits, we've always been zooming in on a specific x value. But today, we're going to do the opposite. Instead of asking, what happens near a point, we're going to ask, what happens when x gets really, really big or really small? This idea, which is limits at infinity, helps us understand the long-term behavior of functions. And it leads directly to one of the most important ideas in graphing, horizontal asymptotes. So before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. Now let's start with our definition. Let f of x be defined on some interval from a to infinity. Then, the limit as x approaches infinity of our function f of x is equal to L means that the values of f of x approach L as x gets larger and larger. So note, we're not saying that x ever equals infinity because that's impossible. Infinity is not a number. All we're saying is that as x becomes larger in the direction of positive infinity, the value of f of x is getting closer and closer to L. Similarly, instead of going towards positive infinity, we can also go towards negative infinity. So we would write that as limit as x approaches negative infinity of our function f of x is equal to L to describe that as x becomes more and more negative, our function f of x is getting closer and closer to L. So let's go ahead and take a look at a couple of examples. So here we're going to have two graphs, one for e to the x and one for 1 over x. So let's just go ahead and draw both of them on the right side. So the first one that we're going to draw is going to be e to the x. Now e to the x looks something like this. So this here would be y is equal to e to the x. And then the other graph is 1 over x. So that graph looks something like this on the left side, and on the right side, it looks something like that. So this here is y is equal to 1 over x. So now let's go ahead and determine the following limits. The first one is the limit as x approaches negative infinity of e to the x. So from this graph here, we can see that if our x keeps going towards negative infinity, the graph is going to approach 0. It's going to get closer and closer and closer to 0. So therefore, the first limit here is going to be equal to 0. Now what happens as x approaches positive infinity? Looking at the graph here, we can see that we're going up. So this means we're not going to reach a particular value because it's just going to keep going higher and higher. So therefore, the second limit would be infinity, or you can say that it does not exist because it is not equal to a specific number. Now the limit as x approaches negative infinity of 1 over x is the behavior of this green graph as we approach negative infinity. So from here, we can see that we're going to get closer and closer to 0, which makes sense because if x is a really large negative number, then 1 divided by that is going to be a very, very small negative number. So the limit here is going to be equal to 0. And similarly, for limit as x approaches positive infinity of 1 over x, that is also going to be 0 because we're just going to get closer and closer to 0. So therefore, the limit here is also 0. So the idea here is if we're looking for the limit as x approaches negative infinity, we're looking at the behavior of the graph on the left side and what happens if we keep going towards the left. And if we're looking for the limit as x approaches positive infinity, we're looking on the right side of the graph and what happens if we keep going towards the right. Next, we're going to talk about the definition of a horizontal asymptote. The line y is equal to L is called a horizontal asymptote of the curve y is equal to f of x if either limit as x approaches infinity of our function f of x is equal to L, or the limit as x approaches negative infinity of our function f of x is equal to L. One important thing to note here is that these horizontal asymptotes only apply to the far right or left of a graph. It doesn't state anything about the middle of the graph. Now let's take a look at how we can find the horizontal asymptote of a function. So to find the horizontal asymptote, we would check the limit as x approaches infinity of our function f of x, and we would also check the limit as x approaches negative infinity of our function f of x. So here our f of x is this rational function up here. So that means we're going to find the limit as x approaches infinity of 3x squared minus 5x plus 1 over 2x squared plus 7. So first of all, intuitively, if x is a really large number, we can see that the terms 3x squared and 2x squared are going to take over, and that these other terms don't really make a difference. Meaning that if you think about x being equal to, let's say, 1 million, then 3x squared is going to be 3 times a million squared. And if we subtract 5 times a million from that, it's not going to make much of a dent. So that means when x is approaching infinity, all we care about is the 3x squared over 2x squared. And that simplifies to 3 over 2. So that's how you would think about it intuitively. But algebraically, what we want to do is we're going to divide all the terms here by the highest degree term in the denominator. So the highest degree term here is x squared. So therefore, this is equal to the limit as x approaches infinity of, we will have 3x squared divided by x squared, so that's just going to be 3. And then we have minus 5x divided by x squared, so that simplifies to 5 over x, plus 1 over x squared. And then now our denominator is going to be 2x squared divided by x squared, so that'll be 2. And then we have plus 7 over x squared. Now using the limit law that we covered in a previous video, we can apply this limit to each of those terms separately. But I'm not going to take the time to actually write that out. But think of it as you're applying this limit to each of those terms. So what's going to happen is any term with an x in the denominator is going to turn to 0 because we have a number divided by a really large number on the bottom. So therefore, this term goes to 0, this term goes to 0, and this term also goes to 0, which means we're left with 3 over 2. And that was the answer that we got when we were working through it intuitively earlier. So now for the other limit, where we have limit as x approaches negative infinity, we can see that it's actually going to be the same number because we would do it the same way, but then all of these terms would still go towards 0 if they're being divided by a really large negative number instead of a really large positive number. So therefore, we only have one horizontal asymptote, and that is y is equal to 3 over 2. Next, let's take a look at a harder example. So we want to find this following limit. So following what we did in our earlier example, we know we want to divide every single term by the highest degree term of the denominator. And the highest degree term in the denominator is x. So therefore, we want to have limit as x approaches infinity of our numerator, which is x squared plus 4x. We want to divide that by x. And then we want to have our denominator, which is x, to also divide it by x. Now this part is fine because that's just going to be equal to 1. But what about our numerator? We have everything under a square root, but we want to divide it by x. So therefore, we need to bring this x under the square root. And when you bring an x under the square root, it's going to become x squared. So then this becomes limit as x approaches infinity of, and then we're going to have the square root of, and this will be x squared over x squared plus 4x over x squared. And now our denominator is going to be x over x, which is just 1. Okay, so let's go ahead and simplify that. So we get limit as x approaches infinity of, this will be the square root of 1 plus 4 over x. And now we can go ahead and bring this limit in, and we can see that 4 divided by x as x approaches infinity is going to be 0. So therefore our answer is going to be equal to the square root of 1, which is just equal to 1. And now let's do a quick recap of what we covered in this video. We learned that limits at infinity is used to describe the long-term behavior of a function. We saw that infinity is not a specific value, it is a direction. Horizontal asymptotes come from limits at infinity. And for rational functions, the dominant terms, or the terms with the highest degrees, are what's going to determine the limits at infinity. And now it is your turn to give this a try. Can you find this limit on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.